these electrical terminals, and 13mm wrench for doing that job. Right. Yeah, now we can reinstall the plasma ring. When we do up these screws, it's just a matter of spin that in finger tight and then a little kind of nip on the ball end. We don't want to crank it in too tight because otherwise when we heat it up, they expand and the screw just gets stuck and then we're in trouble. So electrical connection back on. Need to give that a little pull, make sure it's steady. Now we're good to go for the direct bond. Any questions, anybody? Nope. Anything about anodic bonding? Okay.
Wafers will you be using for direct bonding?
These two silicons. So notice my wafers has only got one side polished.
Is there any outside?
Obviously, hopefully not, no. So obviously the polished to polished side is what the bonding face is. If you want to do alignment, both wafers need to be double side polished. So both sides polished. This single side scatters all the light and you won't be able to see the alignment marks. So you need to have double polished wafers to do alignment with infrared.
So how do you check the bond surface of silicon? If there is a gap or if there is a particle? So you can see
IR photography, IR transmission. I don't have that equipment with me, but
we do have.
if you have an IR camera, you can use that to photograph it. And the ideal method is a scanning acoustic microscope, so that you can generate an image of the bond interface and you'll be able to see any particle voids with that. Okay, so that's clamped. Away we go. Right, so I'm not going to pump all the way to high vacuum with this time because I don't want to dehydrate the wafer surfaces. So all I'm going to do is pump it directly to 1 millibar using the pressure control system. I need 1 millibar for doing the plasma. Generally speaking, we want to try and minimize the time that the wafers spend under vacuum. The longer they're under vacuum, the more dehydrated the surface. You can rehydrate the surface using this, but then what happens is you get voids form. So there's a trade-off between bond strength and voids. So when the more water there is on the surface, when you come to do the annealing, it will generate hydrogen gas when it does the annealing. If you've got a patterned wafer with channels to the outside that the hydrogen gas can escape along, you're fine. If you haven't, you're going to get bubbles in it basically, and you'll have voids of hydrogen gas. So there's a trade-off between, like, if you use water injection, you'll have a higher bond strength with more voids, and if you don't use it, you'll have less bond strength but fewer voids. So there's a kind of trade-off which is more important to you. Right.
I have a question about
Yep.
anodic bonding.
Okay.
Can you use like plasma to enhance the bond?
Generally speaking, it's not really necessary because you generally get a very high bond strength anyway with anodic bonding, but it won't do any harm. And I do know other labs that have done that have used plasma. So yeah, you can use it, but I don't know how big of a difference that's going to make. I've never measured it. So yeah, I've just set my control pressure to 1 millibar and switched it on. You can see the arrow turned blue and it's moved to the position where I've set it. And the software has now taken control of the isolation valve and the pump, so it's going to do its thing now.
You need this every while, Todd. You must be dipping up and down all day.
No, I'm fine, I'm fine. Direct bond doesn't take very long anyway. Where are we at for time? It's about 3:30, not too bad. Yeah, it's going. We're rallying through this quite well.
Do they put any absolute numbers on these micrometers, or are they just whatever it is?
Yeah, I think generally we measure it and whatever it is, it
They
is.
zero it when they're
I
bottom.
Yeah, I think you could potentially make a note of what these numbers are and use that to set your leveling, but I just use it as a feed through. It's not really, it doesn't really do anything. In fact, I don't even know if there's a marker anywhere on the body of this.
Yep.
If there is, you probably covered it up with these stupid labels.
And do they have any procedure or jig to make sure these are vertical
Yes.
in the factory?
No, I think there is a procedure that you can use. I think that procedure is detailed somewhere in the manual.
Okay,
I'll
that's
I'll
good.
get back to you on that.
Yeah.
I don't know how good that procedure is. It might be a matter of like mucking around with a set square or something. But it's not. It's no. Future iterations, we're going to have the goniometers for squaring those up. So if they're not built quite square to each other, then you better adjust it. Yeah, there's not really a great deal of adjustment if they're not square this way. So you're dependent in that case on the rear halves of these clamping brackets. There is some adjustment in that, but you're basically in terms of like take the lens tubes out, screw around with
I'm
it.
gonna get microns.
It's hopeless.
But you're looking, what, 150 millimeters or so, right? Down to the wafer? Well, maybe 100. It's a pretty big distance.
Yeah. We have 7 millimeters of sort of focal range within the chamber. So I think what we're actually catching is the tail end of what it can see.
But if you get just a hair out, it's gonna
Yeah.
be huge. Yeah.
So when we're doing the control separation, we sort of move this up or down, and then the image just sort of goes
See
over
the
here.
shadow. Yeah.
Well, it just moves. You can see it move.
Okay.
So you focus on the lower wafer, move it up. In theory, when you move this up, it should still be in the same place. It's not. It's just moved across the screen somewhere. So either the manipulator is moving like that at an angle, which it isn't. That kind of is square. We build that all square, and or rather, this slider is not completely square.
Right.
In fact, we have also seen this kind of, it wobbles on the way up, and it wobbles by a good couple hundred microns in some cases.
Rack and pinion.
Yeah, it's not really fit for purpose, to be honest. But we're working on it. We've got a bet. There is a much better design.
As long as you can align, right?
It's under development.
Yeah.
This is good enough for doing alignment, and it's been good enough for 90 machines that no one's noticed it. A couple of I think machine 86 was when we tried to do this image capture separation. That's when we noticed it wasn't really good enough.
Yeah.
So now we're working on developing that. We've got the development jig. It's going through some trials, and
The deal I do with the Seuss's with that photo mask I showed you, that works pretty well.
yeah.
You just focus on the reflection in the image and you make sure they're on top of each other and you're lined up.
Yeah.
That one is I mean, you cannot do. This one you can do on loading. The other one is probably going to be direct loading.
Which? What's what?
Because we are talking about processing.
Okay.
If you see when you do direct loading, like it must be but that's not your problem. This is if you just make a wafer like this with silicon, like everybody's already happy. You don't worry about that. Yes.
No, but like all this project is about bonding, like aligning three wafers together using this tool, right?
Yeah, but it's a different type of story. There, the whole project has, I think, four steps of bonding. Four, really.
Yeah. You had a fixture for 3 wafers, right?
Triple stack bonding. Yeah.
Steps of bonding.
So with triple stack bonding, you can do glass, silicon, glass,
Yeah, you know.
or silicon, glass, silicon.
Look, we purchased this
Is
Right.
it only for
to
another
be able to do this
Yes.
manipulation.
So you can do a triple stack anodic bond.
And
Yeah.
SPS, yeah.
Do we have it now or it's not?
SPS, right?
Yes, I think you do have that.
Yeah, because we purchased the fixture.
Yeah.
Yeah, that is here, I believe. Yeah.
Later on, like let's say we succeeded with this, we made
We did 3 like glass wafers with direct bonding.
very good.
With direct bonding, you can. Yeah. With direct bonding, you can do as many wafers as you like.
Can we
Now
use
we
the
have to
same
bond them
fixture
together,
or
Yeah.
that fixture? Is
That fixture, you don't need it for direct bonding. You would need it for triple stack anodic bonding.
Very well.
So the fixture is so that you you do an anodic bond, you have a glass silicon bond, then you invert that, you have the silicon sort of in the middle,
Something for that.
and the fixture makes contact with the silicon wafer to ground it. So then you can do another glass to silicon anodic bond with the silicon grounded. And if you do it with silicon, glass, silicon, how does that work? You do the anodic bond,
Probably this one.
then
Yeah.
you don't need to use the contact at all then.
The main part.
You put a silicon wafer in the upper,
If you remember the device,
do the bond as
So it's
normal,
not
yeah.
at the same time. 2 different.
Two separate bonds, yeah.
All this information is saved in the log file. So
Yes.
I could email it off to Todd in UK. I got an issue and you can look at it and see what you think.
Yep. Okay, we've achieved 1 millibar pressure control here. So now I'm going to switch on the plasma. We can see we have 100 milliamp current flowing, so I know the plasma is lit. I know it's working. It's struck.
Can we use the webcam to see?
Yeah, I was just going to do that. Good point. Yeah.
Yeah, very curious.
The picture is rubbish from the webcam, but you can just about see a little purple smear there.
You still keep separation right now 5 millimeters.
Yes, yeah. Actually, if I...
Isn't it supposed to be higher?
Yeah. You're right. Absolutely right. There you go. Yeah, the larger the separation, the better. It'll allow the plasma to diffuse more
And 50
efficiently.
millimeters is the max.
I think 28, this system's going to bottom out. Yeah, if we... Yeah, you can just about kind of see the plasma here. Yeah, no, that's really making much difference. I forgot to mention, when you switch the plasma on, it will automatically start this timer. If I was sensible, I want to run it for 10 minutes. If I was sensible, I would have put 10 minutes in here before I started it. But I forgot about that, so I have to put up with it flashing red now until until it reaches 10 minutes.
And then you're just gonna... What are you going to do after it reaches 10 minutes?
Switch off the plasma and then contact the wafers. In fact, no, I might not do that. I might actually contact the wafers with the plasma still on. So, contact the wafers with them still in a kind of active environment, and then when they're contacted, there's no point having the plasma on, so I'll turn it off. And then for this direct bond, all we need to do is apply a clamping force of 500 newtons for 5 minutes. We say 5 minutes, in actual fact the bond's going to propagate in about 10 seconds. But just in case it's a slow bond, we're going to give it 5 minutes, which is like more than enough time.
Can you repeat it again why it's 10 minutes for plasma?
It's kind of arbitrary. It's what we've kind of discovered is enough to activate it, but not for so long that the wafer dehydrates. So it's just kind of been determined by experimentation.
And you have the pin is pressing on the...
Not currently, but I will engage it before I make contact. In fact, I might engage it now. In fact, it is engaged now. Yeah, so 10 minutes we find, yeah, it's enough time. You can run it for longer, but the more time the wafers spend under vacuum, the more dehydrated they are, the more, the weaker the bond strength is going to be. So if you want to do a lot of activation, you may have to use water to rehydrate the wafer, but then be prepared to accept some voids. So it's all a sort of a trade-off.
How do you do it? You just do the vapor valve, or
What you would have to do is...
right now you don't have water? So
No, I know. Right now I'm not planning to use it. If I was planning to use it, I'd have this half filled with water. During the initial pump down, I'd have opened this vacuum valve, which would evacuate the headspace.
yeah.
And then once the pressure reached about 10 millibar, I would have turned that off. So then the vacuum there is retained. I would have then had to do what? After the plasma, turn the plasma off, close the gate valve, switch the pump off, close the gate valve, so just isolate the chamber and then open this vapor valve, and then that would expose the chamber to 10 millibar of water vapor, saturated vapor pressure for water. That would then rehydrate the wafer surface.
Is there a way to bond like smaller wafers, like 2 inch or 3 inch?
3 inch, yes.
2 inch. No.
Correct.
We cannot do the alignment. 2 inch.
No. Yeah, I mean with 2 inch, if you just stack them up with no alignment, you could do it. 3 inch, you could do. No, you don't have a 3 inch wafer clamp. You need another wafer clamp assembly, which we'd be able to send you. But yes, in theory, you can do 3 inch wafers, and you could be able to do alignment with 3 inch wafers. So on the lower platen, there was a mark where we align the flat. There's another mark further in to align the flat of a 3 inch wafer. And similarly on the upper platen, there's the 2 holes where the screws are. There's another set of holes further in for holding 3 inch wafers. But you also need a wafer clamp with a longer nose.
But will these viewing ports will cover the 3 inch?
Yes, I think so. Yeah. In fact, yeah, I'm pretty sure they do. I've done 3 inch wafer bonds before.
What is this?
That's
This
it.
is the 4 inch,
For 3
3 inch here.
Yeah, and then these are the holes for the screws to clamp a 4 inch wafer. These are the holes for screws to clamp a 3 inch wafer. Then the nose of your wafer clamp currently sits kind of along the same as this radius. So it sits about here. The nose of a 3 inch wafer clamp would